Now that we've got some familiarity with what polar coordinates are, we're going to take a look here at some graphs that we'll see over and over as we work within the polar coordinate system. We'll start off with a look at equations that give us circles and spirals. So our first one is of the form r equals a. That equation gives us a circle centered at the origin, or at the pole in this case, with radius of a. So you can see in the animation as a changes, so does the radius of the given circle. Our next group is equations of the form r equals a times the sine of theta. And we'll see here that this gives us a circle with diameter a, and the center is at 0, a over 2. So these circles are centered along the y-axis. Equations of the form r equals a cosine theta look similar but are slightly different. Here we'll see that it's the polar axis that goes through the center of the circle, so that the center is now at a over 2, 0. They still have the diameter of a, as in the previous case. Last but not least in this group, we have equations of the form r equals a theta, which is the Archimedean spiral. Here a determines the radius of the spiral. The spiral increases in radius by 2 pi a for every 2 pi degrees you move around. Our next group is the Limacons. We'll start with ones that involve sine. So we have r equals a plus b sine of theta, or r equals a minus b sine of theta. Notice that the sine, that's sign of b, determines whether or not the preponderance of the shape is falling above or below the axis. Also notice that the relationship between a and b drives the shape of this, so that when a is smaller than b, we get an inner loop. When a is equal to b, we get a heart shape called a cardioid. If a is bigger than b, our limacon has a dimple. If a is bigger than 2b, our limacon is convex. When the equation for the limacon involves cosine instead of sine, we can see that b, the sine of b, sign, controls whether or not the preponderance of the shape is falling to the right or the left of the y-axis. The same rules hold true for a, so we get an inner loop for small values of a compared to b. When they're equal, we get a heart. When a is bigger, we get a dimple. And when a is bigger than twice b, we get a convex limacon. Our next group are the roses. These are of the form r equals a sine n of theta, or r equals a cosine n of theta. In this case, a is going to determine the length of the leaves of the rose, and n is going to determine the number of leaves. So if n is an odd number, then the rose has exactly n leaves. But when n is even, the number of leaves jumps to 2n. The cosine and sine impact whether or not one of the leaves lies with its center along the x-axis, as in the case of the cosine, or along the y-axis, as in the case of the sine. Our last group is the Lemniscates. These look like infinity symbols or figure eights. And we can see here they are the form r squared equals a squared sine 2 theta, or r squared equals a squared times cosine of 2 theta. A controls the length of the shape, and then graphs that involve cosine, we can see that they lie with their center along the x-axis, whereas Leminscates involving sine are tilted slightly on the diagonal. Wrapping up, we've got 4 important groups of polar curves that are important to understand. The circles and spirals, which are either of the form r equals a sine theta, or r equals a cosine theta, or in the case of the spiral, r equals a theta. The Limacons, which are r equals a plus or minus b sine theta, or r equals a plus or minus b cosine theta. The roses, r equals a sine n theta, or r equals a cosine n theta. And then finally the Leminscates, which are r squared equals a squared sine 2 theta, or r squared equals a squared cosine of 2 theta.